Welcome to IIT Gandhinagar. So we are very delighted to have a very distinguished visitor, Professor Thanu Padmanabhan from Inter-University Center for Astronomy and Astrophysics in Pune. Many of you know about PADI. Professor Padmanabhan is an internationally acclaimed theoretical physicist who is very well known for his seminal contribution in the field of gravitational physics, cosmology, gravitational physics, cosmology, astrophysics, you name it, quantum field theory, why not? His research work spans a wide variety of topics, including everything in gravitation, quantum field theory, quantum gravity, and he has made several crucial contributions related to the understanding of what we call the dark energy and also the interpretation of gravity as an emergent thermodynamic phenomena. In fact, in recent years, his own approach to quantum gravity, what we now call in the literature the emergent gravity approach, led to many important and extremely significant results, which I hope many of things Paddy will discuss here. Professor Padmanabhan has a very distinguished career. He has received several national and international awards, including Shanti Swarup Bhatnagar Award in 1996, G.D. Wilder Award, Infosys Science Foundation Prize for Physical Sciences in 2009, Third World Academy of Sciences Prize in 2011, and also Padma Shri from the Government of India in 2007. He was a distinguished astronomer visitor in the Institute of Astronomy in Cambridge. He was a president of the Cosmology Commission of the International Astronomical Union, chairman of the Astrophysical Commission of the International Union of Pure and Applied Physics. He was elected fellow of all the three academies and as well as of the Third World Academy of Sciences. Well, apart from being a very distinguished physicist and a scientist, he is also a very acclaimed in fact, he contributed significantly to the science education in our country. He has authored several advanced level textbooks, which are basically the standard textbooks in any leading university of the world. They are considered to be pioneers in the books in the field of astrophysics, cosmology, and general relativity. Not only that, he has also co-authored several popular level science books. In fact, his articles for science students in the journal Resonance on various aspects of fundamental physics considered to be a classic in science education in India. In fact, these articles were, and in fact, even today, they are the motivation of many of the students, including many people here, to take up a career in theoretical physics and physics. I strongly suggest any of the students here to look at his homepage and particularly look at the articles, Resonance article. I mean, they're really, you can learn a lot of things from them. So we are very grateful that Professor Padmanabhan has agreed to spend time with us, and I welcome him to deliver this colloquium titled Avatars of Gravity.
Thank you, Sudipta, for a lovely introduction, and this is my first visit to this place, and I have been enjoying it quite a bit, and I'm very thankful to the institute and the director and to the department people for making it so pleasant. So this talk, I was not sure what kind of audience to expect, and Sudipta told me that it will be a very broad spectrum. So the talk is accordingly kept like that. So the criterion I used is that anyone who can read a graph should be able to understand most of it. But I'm also throwing in a little bit of extra stuff for the experts in the audience or theoretical physicists. And if you ignore that part, you will not lose anything if you don't do this for a living. I mean, you can ignore those parts and the rest of the things will flow on its own. So there are track 1 and track 2 going through the talk. So let me start by sort of talking about what are the avatars of gravity I'm going to talk about. So the first avatar of gravity is embedded in the structure of physical laws itself. So that is a good place to begin. So we originally thought that the Newtonian gravity, which we all know and love, is all there is to gravity. But then at the early period of 20th century came two more revolutions, special relativity and quantum theory, and then all the crisis started. To begin with, you wanted to combine quantum theory and special relativity, which you might think has nothing to do with this, so I have kept this out for the moment. But there are going to be things which come from here for our talk, so let me just do this. This leads to something called quantum field theory. And this is exactly what we use to describe all of microphysics. So there is a standard model of particle physics, which is extraordinarily successful in explaining observable phenomena at the level of microscopic physics and constituents. In addition to that standard model, there are two major predictions when you combine special relativity with quantum theory. The first is there is something called vacuum fluctuation. This is, of course, an artist way of thinking about it, that what you call empty space is filled with virtual particles and virtual energy fluctuations, and this goes on. This is going to play an important role in cosmology much later on, so that is why I am introducing it right here. And the second one is that to every particle there is an antiparticle. The reason I mention this is that usually people think that when you go from an approximate theory to an exact theory, the predictions of the exact theory will come when some parameter is large. For example, if you take quantum mechanics and you assume it is sort of non-relativistic, and when you go to something which is close to speed of light, then relativistic phenomena will appear. It is not always the case. There are very often when exact theories leave a relic at very low energies, and the antiparticle is one such example. To say that an antiparticle exists is a statement which is not relevant to energy. Of course, if you want to create it, you may need relativistic energies, but the existence of an antiparticle is a firm prediction which comes up when you combine special relativity with quantum mechanics, which exists in an energy independent way. We will see examples of such phenomena even later on in the talk, so I just thought I will mention that here. So this is all extremely effective, and I really believe that if you just want to shut up and calculate, you can calculate everything and it will all agree with experiments to an astonishing precision. But no one can really accuse quantum field theory of being elegant, let alone complete. So there are issues which we don't quite understand, but we know how to go about doing things without worrying about it. In sharp contrast, when you combine special relativity and Newtonian gravity, you get a theory of absolutely brilliant elegance. So people have said this, several people have written poetry about how great general relativity is as an elegant theory. My most favorite quote, and in fact I think this is the most beautiful compliment ever paid to general relativity, is this sentence. It represents probably the most beautiful of all existing physical theories. When you read this, you won't feel very impressed. It is not very poetic, it is a very straight, simple English statement. The reason I consider this to be most important has nothing to do with the sentence, but where I took it from. It is taken from volume 2 of Course of Theoretical Physics by Landau and Lifshitz. Now, if you are familiar with this book, this is a book in which not a single punctuation mark is wasted, let alone a word. Okay? It is all physics, 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 extremely terse. So these guys come to Einstein's theory, they just couldn't move ahead without putting in this sentence. And that, I think, is the power of general relativity, and it is probably the greatest compliment you can pay to general relativity, that these guys were forced to say this, who don't waste a single word, has this sentence in their book. Now, why is it so beautiful? It is beautiful because starting from some extraordinarily simple ideas, the principle of equivalence and special relativity, which I can teach you in 15 minutes, Einstein conjures up this theory that gravity must be the curvature of space-time. This is really the genius of Einstein. Rest of it, as they say, if you're a chess player, you will know, rest of it is just a matter of technique. Okay, many people could have done that. And here is exactly where the genius comes in. Since it is so beautiful, I will spend a little bit of time explaining this to you. The first result is the one of time dilation, which is taught in different ways, but I like to think of it like that. You put a clock on the table that is called a reference clock, and when that reference clock shows a time interval dt with a reference r put in there, there is another clock which is moving around, and it moves a distance dx. In that case, the second clock will show this time. So you take this time and then subtract from it, you divide by c if you want to, the time light takes to travel, the distance the clock has traveled. So this actually shows you that this is going to run slower compared to this with this minus sign. So this tells you what happens when something is moving. So you take a clock and put it in a rocket ship and shoot it up with an acceleration g. Then you can compute everything about this clock using this, because this is just moving and special relativity tells you what happens there. What principle of equivalence tells you is that this is equivalent to this. If you have that rocket ship staying put in a gravitational field g here. Therefore, if the time slows down here because of motion, time should slow down in the presence of gravity. And in fact, for a very weak gravitational field, it is very easy to write down the expression. This is Resnick and Halliday. Capital V square is V square plus 2gx. And 2gx is twice the gravitational potential with a minus sign. So you just go back here and this you replace by V square times dt square. So you get that original c square dt square, then you get this and this. You combine them together and you find that the c square dt square is just 1 plus 2 phi by c square times this reference clock time minus this. What is the reference clock time now? You take a point where phi is 0 and there this and this will match if things are not moving. So this reference clock time is the clock time at an infinite distance from a particular body. What this represents on the right hand side when you have multiplied it by this phi, which in this weak gravitational field could depend on time and space, is a curved spacetime. So all the mathematicians knew that this is going to represent a curved spacetime. So this phi is sort of some g naught naught, as the mathematicians call the metric tensor. So this phi corresponds to this GAB. And this fusion of metric and gravity is considered to be the most beautiful achievement of general relativity. This is again from, like Landau and Lifshitz, this is from Pauli, who can be very nasty and is fairly economical with price, but he had to say this again when he wrote the review. And this is indeed true, and this is a major aspect of general relativity. So this is the sort of second avatar of general relativity. Then of course this just tells you what kind of metric you have if there is phi, and that phi is determined by Newtonian del square phi is equal to rho kind of Poisson equation. In Einstein's theory, there is an engine which sort of drives the geometry, and that equation is, which has more subscripts than something like this. So if you don't know general relativity, you can worry about that. The physical aspect of general relativity is captured by rewriting that equation in a different way. This I want to spend some time because I know general relativists who have been in the field for 20 years, they didn't know this. So let me spend a little bit of time. It's a very beautiful result. What it tells you, which everybody knows, is that if there is a body here, it curves the spacetime around it, and this curvature of spacetime is what you call gravity in Einstein's theory. A very, very loose analogy is that if you think of this as a mattress and then you put a ball here, the mattress gets curved, you put another small ball here, it will roll down. So if you haven't seen the mattress, you will think that this ball is being attracted towards it, and that is your gravitational attraction. You can think about this. It's not very accurate, but you can think about it. A more accurate statement is that if there is some amount of energy density at a given point, then the radius of curvature, if the curvature is mild, radius of curvature is large, and if it is curvature is strong, the radius of curvature is small. So 1 by the radius of curvature square is proportional to rho except for some constants. Now this is an exact equation. That is, this single equation is equivalent to 10 equations of Einstein. It's not an approximate hand-waving argument. And for those of you who haven't seen this, this is what I said, there are general relativists to whom this comes as a surprise. So this page is only for those who know GR. So what happens is that in Newtonian theory, you write del square phi is equal to rho, and mass and energy are equivalent, so this should be energy density. And the energy density measured by an observer with a velocity, forward velocity UA, is given by TAB UA UB. Now we want to generalize it. We had already seen that phi goes to a metric tensor. So you are looking for second derivative of the metric tensor. So what happens is that there is a rigorous way in which you can take something called a curvature tensor and project it to the spatial part. Remember, del square only has spatial derivatives. So you can project it to the spatial part and get a spatial curvature tensor. Then from that you can define a curvature scalar, and r to the minus 2 will be its dimension. And that will turn out to be this quantity, and this rho equals, this is equal to the energy momentum tensor. if you equate this radius of curvature of in the space orthogonal to the observer to the power -2, this quantity, equal to the energy measured by the same observer, and you insist that this holds for every observer. So that is why it is a single equation, but it has a UA hanging around, and it should hold for all UA. That gives you an identity that TAB should be equal to GAB. So from that you can reproduce all of Einstein's theory. So this is an exact one equation equivalent of Einstein's theory. This is important because later on we will find that. So here I have brought in something which you might call the observer dependence. Both this quantity and this quantity depends on which observer you are talking about. That is a feature, not a bug. So if you write down a single equation and insist that it holds for all observers, that is equivalent to having 10 equations. So many times it is easier to interpret these kinds of objects in an observer dependent way rather than try to do this in a completely observer independent way. And that is an important lesson which we will carry forward. So this is what you get in general relativity. So you have one thing here and one thing here, and naturally you want to put them together, and that should get you something called quantum gravity. And of course we don't have it yet. It is a kind of an unknown final frontier. But what I am going to stress today is that there is going to be a cosmological tilt to this talk. What I am going to argue that it is needed in cosmology and can also be tested by cosmology. I mean, usually people lament that quantum gravity cannot be tested, and they even make a virtue out of it that physical theories need not be tested and there is a different paradigm, blah, 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 blah. That is all nonsense. Physical theories, if it doesn't make a prediction which can be tested, are not physical theories. They are beautiful mathematics or excellent philosophy, but not physics. So it can be tested if you are sufficiently clever, and it can be tested by cosmology. So this we will indicate as we go along. Now there is another reason why general relativity has to be incomplete, and you need possibly a quantum mechanical completion for general relativity. For this, I have written 3 major theoretical challenges faced by general relativity. The first is what is called the black hole singularity. We will elaborate on it in a minute. The second is the emperor has no clothes question, which come up whenever you give a popular talk in cosmology. You give this talk and somebody puts up the hand and asks you what happened before Big Bang. Now the honest answer to that question, which I had always given, is that we haven't the faintest clue. We should figure it out, we are working on it, we don't have an idea. Most of the time people cheat. So they will tell you all kinds of things like, that is when the entire space came, therefore this, etc. The fact of the matter is we don't know the answer. Here it is almost like the Rayleigh Jeans days of black body radiation. You have a rigorously defined theory producing manifest nonsense. So you needed quantum theory to correct it. You need something else to correct this. I mean, you find that something which should be finite is infinite in general relativity. So that is something which we will talk about, and at least I will try to give you some speculations as to what the new idea avatar tells you about that. And the third is something called a cosmological constant, which as we go along I will describe in greater detail. So let me start with the first one, this black hole collapse. So this John Wheeler was probably the first guy to emphasize it so strongly. He says that the predictability gained by science is lost at the black hole. This is very, very clear statement operationally. You take a neutron star or some compact object which is going to collapse to form a black hole. Now you put one of, I mean, we all have such colleagues. You put one of your colleagues on the surface so that he will collapse into the black hole. Okay, you persuade him. Now that guy comes and asks, okay, I'm willing to do this for you, but you tell me what is going to happen to me, because we are going to lose communication very quickly. So he has a watch and he says, okay, what is going to happen after 1 hour, after 2 hours, after 3 hours, after 10 hours? So you do your computation, and the best answer you can give is the following. Okay, this is going to happen, this is going to happen. At 10.7 hours from now, I don't know what is going to happen to you. That is the fact. We really do not know how to predict your not so friendly colleague's fate when he is willing to collapse into a black hole. So that means it is just like saying that when I throw a ball up there, I know where the ball will be up to 14 seconds, 14.1 seconds. After that, I don't know where it is. It is as bad as that. So that is a major issue. So when anyone tells you that we have a theory which has solved the problem of the black hole, you should ask him what happens at the singularity. Okay? Until you give an answer, we have not solved the problem. So it is incomplete. The most popular answer to this, which I also believe, which Wheeler also believed, is that there is a quantity with the dimensions of area you can construct from the three fundamental constants, G, H cross, and CQ. It's a very tiny area, 10 to the minus 60 centimeters square. And when this quantum of area is the sort of surface area of the collapsing object of that order, or the length of the collapsing object is the sort of square root of this, quantum effects has to be important, and that has to do something to this and modify the physics, which is very likely, but we need that. The second result is, which is this Big Bang, which I was telling you. Let me elaborate a bit on that. One of the major predictions which comes from this is that the universe is expanding, and the time it takes for the universe to double its size is like the radius of curvature, r curvature, upon c. Now, if this r curvature is constant and if this rho is constant, this is like investing in some whatever, NSE or whatever. Every 7th year, your money doubles or whatever. So this is going to happen. But of course, what happens is that as the universe is expanding, the densities are going to drop, which means that this r curvature is going to go up. So the time for doubling is also going to be higher and higher. When the universe was like 1 second old, it was doubling very rapidly. Now that the universe is old and tired and it is like 14 billion years old, it is not doubling so rapidly. And this is how the universe is expanding. And we have fantastic evidence that this is a true picture, because this is all completely confirmed by observations, because cosmology today is entirely driven by observation. There is something called the cosmic microwave background radiation. So this is the relic from the hot phase of the universe, and this radiation is coming towards you, and it is as though you are sitting inside a microwave oven which is kept at the temperature 2.73 Kelvin from all directions. This is filled with a Planckian radiation. And this comes because at some time the radiation decoupled, and this is coming from a time when the universe was 1,000 times smaller. So we can directly observe what the universe was doing 1,000 times smaller. I mean, this is something fantastic which happens only in cosmology. When I look at one of you, I don't see you as you are right now, because light takes some time to come from there to here. When I look at the sun, I see the sun as it was 8 minutes earlier. So the further I see, the earlier I observe. So by looking further and further into the sky, I can see what happened at the earlier phases. I don't have to speculate. If my technology is good enough to observe, I don't have to speculate. It will tell me exactly what the universe did. I only have to put it together with the physics. So that is what I have illustrated here. You are sitting here. This is your sky dome. And when you go radially out, if you go sufficiently far away, you are going to hit a time when the average energy in the universe was about 1 electron volt. And that is the time from which your cosmic microwave background radiation is coming to you. And in principle, if you are using some neutrino physics or something, you can go still further and you will get the electro-wave phase transition in the sky. So you are only limited by technology. Come up with a brilliant neutrino detector, which is as good as photon detectors today, then I can see what happened at the electro-weak phase transition in the universe, in the sky. It is imprinted for you. Go still further, you can see whether there was a grand unification scale and anything happened. Still further, you can see quantum gravity on the sky. What happens when you go to Planck energies or Planck skies is imprinted in the sky. We are not being able to observe because all electromagnetic observation sort of ceases here. Neutrino can take it up to this point, and then you need higher and higher energy probes to do that. But in principle, nothing prevents you from seeing the effects of quantum gravity on the sky. It is imprinted there. And in fact, this phase, and outside is what we call now Big Bang. This is the Big Bang, where the quantum gravitational effect should modify. The ideas, which I will describe later on, suggest that there was a phase transition. There is one phase here, which you may think of like ice, and this is the phase which is water, and a phase transition has taken place. And the fluctuations in this pre-geometric phase is what you are going to see, the fluctuations here. Okay. So that is all for the smooth expanding universe. And what happens to real universe? Real universe have structures like galaxies, and you want to know how they got formed. So the easiest thing would be to make a universe in your computer. So if you start with small inhomogeneities, and as you roll the time on, which is going on here, you find that just because of gravitational instability, matter comes together, and it forms the kind of structures which you see in the sky today. This kind of things has been going on now for several decades, and the computers have become very sophisticated. So you can actually simulate what happens in an expanding universe given the initial conditions. Now, those initial conditions are going to be important for two reasons. Firstly, if you start with a completely uniform universe, it will remain completely uniform and we won't be here. So you need to have slight fluctuations in the early universe in order for this model to work. Now, you don't want to put the fluctuation because that would be ad hoc. But fortunately, remember this picture I showed you, the vacuum fluctuations must exist sufficiently early on, either quantum gravitational vacuum fluctuations or something else. The quantum mechanics will kick in at some stage and that will produce fluctuations. And these are a very natural phenomena in quantum theory. And these fluctuations can grow and form the cosmic structures today. So how do we test this idea observationally? If this is the model, then the fluctuation started at some stage, then it evolved to some value, and then it is today at some other value. And in between, when the universe was 1,000 times smaller, we can actually see it. So that is the cosmic microwave background radiation which you are seeing in the sky. So if this model is correct, then the cosmic microwave background radiation at 2.7 key cannot be completely uniform. There has to be fluctuations in this. And this was a holy grail in cosmology for a long time, and people did find these fluctuations. Many of you would have seen this picture in other talks. And what is remarkable is that you can extract so much of physics out of it. And you couldn't have done this without technology. And that is one important thing about cosmology, that virtually everything in cosmology today is technology driven. So this, I had just given you a comparative slide. This is what happened in 1992 when the fluctuations were first discovered. Roughly 10 years later, you got this, and now you have like a high density TV screen. This is 2013, and things are improving. So all these satellite experiments were specially designed to do this. And this is the way technology is helping you to figure out things about the universe. So this is a more technical graph presenting the same fluctuations, which you see in color here, temperature fluctuations. And from this, you can ask two questions and hope to answer. First is, where did these density fluctuations come from? What is its origin? And the second, can these fluctuations actually lead to the structures we see? Because the picture I gave you is that, let me just go back a bit. Once you have these fluctuations and it is coming here, these structures has to come out of these tiny wiggles, and is that a correct picture? So what we are asking is that you need these vacuum fluctuations in the very early universe, which should lead to this. That if you reverse the arrow, immediately constrains what is the amplitude and the spectrum of this vacuum fluctuation. It has a very special signature, and that you can unravel from studying this. Second, you want to go from here and form the cosmic structures today, and you want to ask whether this works. You start with this, plug it into your computer, and see whether you can get this. So let me look at this part first, because this is just, this is known physics. The energy scales here is 1 eV. It is lab-tested physics. So from here to here, there are no uncertainties. It is just a computational complexity, which you can handle. And you want to know whether this gravitational instability picture is correct. It turns out that this is known to you from observation. This is known to you from observation. If you have to get this from this, it depends on the nature and amount of the matter in the universe. It depends on the composition of the universe. These studies suggest that the universe should have a very weird, tantalizing composition. What you and I are made of, the normal baryons, neutrons, protons, kind of a stuff, the atoms constitute only about 5%. And dark matter is something which clusters at galactic scales, which are not made of these normal atoms. These are non-baryonic matter. We have no clue what it is, but we see observational evidence in the sky. We haven't seen it in the lab. There are experiments underway, and many of us are hopeful that we will find a candidate. So this is another 26% or so, again comes from observation. But nearly 69% of whatever here is effectively contributed by a term in Einstein's equation called cosmological constant. This is what people used to call dark energy, but if you start talking about dark energy, then it becomes Star Wars, Dark Vader, etc., etc. So I don't want to use that word. And it seems that all evidence is consistent with just having a cosmological constant. If you have that, this particular thing from which you want to get the structure implies this kind of a composition for the universe. Now, what is this cosmological constant? So, this cosmological constant, if it exists, then again you want to test it observationally. I told you that everything in cosmology today is observation driven. Now, the feature of this cosmological constant is that it will accelerate the expansion of the universe. That is, if you think of the expanding universe like a car which is moving in a road, then you can have three kinds of motion. The car can be going with uniform velocity, it can be decelerating to a stop, or it could be speeding up, accelerating. So the question is, which of these is true about our universe? So we want to know the expansion rate today, and we want to know the expansion rate in the past when the universe was, let's say, 1/3 its size. So if I know both of them, I know expansion rate has increased, decreased, or stayed steady. So how do I know? You just ask the universe, because if you want to know what happened in the universe when it was 1/3 the size, you just have to go sufficiently far away and observe it. Because I told you that you can, by going further and further in the universe, you can get earlier and earlier part. Now, of course, there is a small catch. When you go and start observing something further and further, light from there dims. So you need either better technology and you need brighter sources. Now, there is an extraordinarily bright source which nature has provided us. This is called the supernova explosion. So many of the stars, especially the large stars, during the late phase, explodes as a supernova, and these are very bright beacons in the sky. I mean, there is the story that Betelgeuse is going to go boom very soon, and if it happens, we will all see this. But in our galaxy, there has been several of them, and this is a very famous nebula called Crab Nebula, which happened in 1054, and this has been observed by several civilizations at that time. The most meticulous records of this was kept by Chinese. I'm sure all of you can read Chinese. So this is the record from the Chinese observers, which says that there was this thing which happened, and it was so bright that it was seen through daytime for a very, very long time. It's a fascinating story, but Wiki has a good article on that, so go and look it up if you want to know more about it. So coming back to physics, every data point in this is a supernova explosion. Now with telescopes, we have so many supernovas, hundreds of them. And using that supernova at way further and further away, you can measure how the universe was expanding at that time. So you can plot the speed of expansion versus the size of the universe. So today, the size of the universe is normalized to unity. It has some speed of expansion. And in the past, you are plotting the speed of expansion. So you put all these data points, I mean, you don't need to do great curve fitting to see that the speed of expansion was decreasing, turned around, and has started accelerating. So this is the accelerating phase of the universe, and this acceleration is driven by the cosmological constant. So a sort of corollary to this is that if you plot the cosmic density as a function of time, the density keeps decreasing. This is again from supernova data, and it plateaus out at a constant value. Okay? It is not very obvious from this whether it continues to decrease or plateaus out, but when you put the data properly, you find that it plateaus out to a constant density. So the ultimate 0-point density of the universe is not 0, but a finite number. This is the density contributed by effectively what is known as the cosmological constant. So this is a signature of the universe. This is a number. If there were cosmologists at a redshift of 8 who are studying cosmology, they would have got the same number as we have got. And dimensions don't matter because you can scale everything to Planck dimensions, and then there is a dimensional number you will get. So the way the universe is evolving, this tantalizing composition I talked about, can be graphically represented like this. This is the cosmic density against the size of the universe. It's some kind of a logarithmic scale. So the normal matter decreases as the universe expands. Something has happened. Is it okay? Yeah. So the dark matter is typically some 8 to 10 times larger, and that also decreases just like normal matter. The radiation in the universe decreases faster, which also means that when you go into the fast, it rises faster. So there is a particular point at which the dark matter which dominates this, and this will have the equal density. So this is another number which I call rho equality, where matter and radiation has equal amount of density, which is a key signature about the universe. Again, my friend who was doing cosmology at a redshift of 8 in a galaxy will come up with the same number for this which I have. So our universe is characterized by this number, and also if I just take the total density, I told you that if there is a cosmological constant, it sort of comes like this and then plateaus. So you have two important numbers I have introduced. One is rho eq and another is rho lambda. These are numbers which we should be able to explain. Why is this universe having these numbers rather than any other numbers? I mean, what fixes its numerical value? And that doesn't change with time. So these are constants for the universe. So there is one more number which I want to introduce, and then we will get into that. I told you that very early on, some fluctuations has to be generated from quantum fluctuations. Its spectrum has a particular feature called scale invariance. That is not too important. Then there is an amplitude which is like 10 to the minus 5 in some dimensionless units. So this is also predicted, this is also something calculable from the cosmic microwave background radiation. And this happened very early on. So let us go back to this picture: vacuum fluctuation, CMBR, and then our universe. There is one density which essentially characterizes this phase, which I have called rho eq, but it is a pure number. Then there is a rho lambda here, and then there is some other number which characterizes when these quantum fluctuations originated, which could be traded off for this amplitude 10 to the minus 5. This is what our universe is. So a theoretician's task is to understand these numbers and explain them. So the rho eq, nobody really worries about it. You can compute what it is, and that depends on the amount of dark matter and amount of baryons, etc. And the feeling is that high energy physics will eventually fix this number. It's not just a feeling. There are models in which this number can be calculated, except that these models are not unique. You can get the number. Once you tell me the number, I can give you a model in which that number comes. But it is not possible to sort of uniquely predict that number. But at least we understand roughly where it comes from. The real problem is this cosmological constant. So this I can again talk in terms of density, but let me talk in terms of the cosmological constant itself, the way Einstein introduced it. It has a dimensions of inverse length square, and I told you that there is a combination here coming from gravity, quantum theory, and special relativity, the three things which we started with: Newtonian gravity, special relativity, and quantum theory. They together form another quantity which has the dimensions of centimeter square. So if there are four cosmic constants or four constants of nature in the picture, and they together form a dimensionless number. So this is a pure number independent of units, and you can compute how much it is. So of course you don't go and compute this number, but you compute indirectly, and you know that it's tiny but non-zero. It is like 10 to the power minus 123. Okay, 123 is easy to remember. Give or take some factor, but that doesn't matter. Okay, this is what observations tell you. Theoretically, we have absolutely no clue. We don't know how to compute it. So unlike the rho eq, the rho lambda and the numerical value of this cosmological constant is something which we don't know how to compute. And this is one of the major problems in theoretical physics. There is another way to look at this, which I think is very fascinating, and it is not often emphasized, so I'm going to spend some time on it. The reason numerical value for cosmological constant, is the audio okay in the back? Okay, fine. So the way it works is that the gravity, which is so gorgeously elegant, blah, 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 and theories which are elegant should have lots of symmetry. Gravity actually goes and breaks a symmetry which exists in all other theories of nature. In all other non-gravitational theories of nature, if you take the Hamiltonian or energy and shift it by a constant, you will not know the difference. The zero level of the energy can be shifted. This is a symmetry of the theory in the sense that if you add a constant to the Hamiltonian or to a Lagrangian, those of you who understand that language, that doesn't change the equations of motion in matter sector. If you add a constant to the Lagrangian, gravitational theory changes. The equations of gravity changes. So the gravity actually breaks a symmetry which exists in the matter sector. And this, in fact, I believe is the strongest evidence why Einstein's gravity has to be modified. It should be made to respect this symmetry. Now, so you would have thought that, fine, it breaks this symmetry. But observationally, it looks as though gravity is completely unaffected by the changes in the zero level. The point is that as the universe evolved, it went through various phase transitions like electroweak phase transition, which changed the zero of energy by a very large factor. They haven't led to any observable consequences. At the same time, today, the lowest energy level plateau I told you, it does go and couple to it because that is what is driving the accelerated expansion of the universe. So why is this happening? What fixes the value of this and how do I restore this symmetry? Okay, it's a very tantalizing puzzle. So just to summarize this part, which involves cosmology, there are two numbers which you want to explain. There is A, the amplitude of fluctuations, and the other is the value of the lambda. In conventional models of cosmology, they don't think these are related at all, but I will try to convince you that they are very close to each other. Okay. So let us get back to the challenges, and one point which I have mentioned is that all of them involves H cross. So which means you have to put together gravity and quantum theory if you need to have a hope for solving these problems. And so you have to quantize gravity. And of course, everybody wants to quantize gravity. I haven't seen a person who doesn't want to quantize gravity. For example, a classic example which I came across is Anna Hathaway, one of the Hollywood actresses. She is interested in string theory. Okay, so the population of string theories is increasing, and she says that she thinks about why space exists and how universe is behaving, etc., in her spare time. Okay, so the lack of effort is not the reason we have not succeeded. A lot of people are working on it, but nobody has succeeded. Okay, so the question is why. Now, in order to tell you why, I want to tell you what I believe is going to happen. We just celebrated the first 100 years of GR. What is going to happen in the next 100 years? The recent work suggests that we have completely misunderstood gravity. And the gravity is what one should call an emergent phenomena. A more technical statement is that the field equations which govern the classical gravity has the same conceptual status as those describing, let us say, elasticity or hydrodynamics. Like, you know, the equations for cantilever. I mean, this is IIT, so I don't have to worry about that. I mean, everyone must have studied elasticity. And if you vibrate something, and it is going to go up and down. And the theory of elasticity can be written down in terms of those equations. And if your engineer comes and asks you what is the atoms and molecules doing, what is the atomic Hamiltonian before he can build a bridge, he's a wrong engineer to go to. Okay, so he need not have to worry about any of that. There is a self-consistent theory of elasticity based on just a few numerical factors like Young's modulus or stress and strain constraints, etc. Given that elasticity has a life of its own. So is hydrodynamics. You just give some parameters and you can describe the flow of any water or any fluid. So the Einstein's field equations have the same conceptual status as this. This also explains to you why, in spite of Anna Hathaway spending so much of time, we have not succeeded in quantizing gravity. The point is that suppose you take elasticity and you didn't know anything else. You know elasticity, you know equations of elasticity, you know the Lagrangian which described elastic phenomena, and you quantized it. You will get fantastically beautiful physics. You will understand phonon-phonon scattering. You will see how phonons are generated. You will understand quantum elastic phenomena, which is essentially phonon physics. But you will not get the atomic structure of matter. So we have been applying the right concepts to the wrong equations. So the Einstein's equations are just like theory of elasticity, and that is where we should be applying this. And we don't know where to apply it. So the first step is to start saying that the space-time dynamics should be described in thermodynamic language and not in geometrical language. This is again a very important thing, and those of you who go and read other papers, etc., and especially those who do GR, Let me tell you that the aim is not to derive Einstein's equation by a thermodynamic argument. That is a dead end. If you use a thermodynamic argument and you get G mu nu equals T mu nu, you are sunk, because the G mu nu is a geometric object. What is thermodynamics doing here? You have to rewrite the entire Einstein's equation in a completely thermodynamic language, and you should speak in thermodynamic language. And the really important question to ask is not so much as why gravitational field has a thermodynamic analog, it is why certain thermodynamic systems can be described by Riemannian geometry. Okay? So that is the right question to ask, and this is the first point which one has to do. Now, if you take that philosophy, at least those who have condensed matter, in fact, this is a famous quote from a condensed matter physicist, and you will realize that there is an important quantity in thermodynamics which distinguishes it from normal mechanics. This is the concept of heat density. In all physics, you have energy, but thermodynamics also have something called free energy. So if you take the difference between these two, you get the heat of that system, which entropy multiplied by divided by the volume, so that is the entropy density. And there is a Gibbs-Duhem relation which tells you that Ts is equal to P plus rho. And those who know GR, there is a way of writing it in terms of null vectors. So normal matter has heat density, which is this D times S. Now, it turns out that space-time also has heat density. What I mean by that is not that you need an exotic space-time by a black hole or any such thing. This place, here, at this point, it has a heat density. How is that? Okay, you do it like this. So you take a point or an event in space-time, this is a space-time diagram, and you shine a beam of light. Now the beam of light is bent by gravity, so it will go in some crazy direction like this. So the light rays are called null rays in GR. Now you go to a guy who is freely falling at this point. Freely falling guys don't feel gravity. I mean, that is, the Resnick and Halliday lift, which is falling freely. Then you don't feel a weight. So those guys will see the light rays going in 45-degree lines, which is what happens in special relativity. So here is this freely falling guy, and he sees something like this. In some local region, this is what he will see. Now you take another guy who is sitting quietly there. So that guy will have a trajectory, and this is something which you can calculate. It turns out to be a hyperbola in this region. Now the remarkable result is that the vacuum fluctuation seen by this freely falling guy at around any point will look like thermal fluctuations to this guy. Okay? So the vacuum appears to have a temperature depending on which observer you are talking to. This guy will say 0 temperature. This guy will say, no, I know what is the temperature. And that temperature will depend on this trajectory which this guy has taken. This is a very non-trivial equivalence, and I can go on and give a complete colloquium on that, but let me not do that. This is probably the most beautiful theory result which we have in the interface between quantum theory and gravity. That is, if you have an observer who perceives a horizon beyond which he can't see anything, and that can happen because the gravity has acted in such a way that light rays cannot go from one place to another, or it can happen because you are following a particular trajectory where you choose to ignore those regions. If you do that, then there will be a temperature which is related to the acceleration either taken by you or to the acceleration which comes out geometrically. So there is this non-trivial relationship that there are observers. Remember, early on I told you that the right way to look up Einstein's theory is for each observer and then write down an equation for a given observer and say it should hold for all observers. So if you take an observer, an arbitrary generic observer, he will see a temperature in the space-time. And since some region is blocked and information is lost and information is connected with entropy, he will also see an entropy density. So he will attribute a heat density to the space-time. Now, once you have this is just like associating a heat density with a glass of water. And incidentally, this is something which everybody knows in the context of black hole, thanks to Stephen Hawking. So you would have read that black holes have a temperature, black holes have an entropy. But what I am saying is that all space-time for a particular observer will have temperature and entropy. And the black hole's temperature is highly observer dependent. The guy who is outside the black hole will see the temperature. A guy who is freely falling inside will not see the temperature. Okay. So all temperature, these thermodynamic phenomena which we are talking about here for space-time related thermodynamic phenomena is observer dependent. So you have this result. And this, why is it so important? Is it just a curiosity? No. It is very important to be hot. Because you could have figured out that if I have a bottle of water, it contains discrete atoms, which are angstrom size objects, without ever running experiments at angstrom size. If you don't believe me, ask Boltzmann, because he is the first guy who figured it out and he didn't have experimental results. At that time, everybody was trying themselves up in knots, trying to understand what heat is. There were all kinds of weird theories going around. It's almost like high energy physics today. Okay, and the Boltzmann came along and cut through all this and said heat is just a kind of motion. There are microscopic entities, which we'll call, well, incidentally, Boltzmann committed suicide, but that is a separate issue. Okay, so these molecules inside it and they are moving, and this moving kinetic energy is what you call temperature. So what he said was that if you can heat something and store energy in it, it has microstructure. And he also gave a very beautiful formula, which we of course teach completely wrongly to kids. The way we teach this formula is that E is equal to half nkt. E on the left side, half nkt on the right side. That is wrong. You should teach it as delta E upon half kt is delta n. This is a very subtle difference because the right hand side energy and temperature are thermodynamic quantities. In the thermodynamic limit, energy exists, temperature exists, energy differences exist. Delta n or number of degrees of freedom has absolutely no thermodynamic meaning. Okay? So, or you can put kb to this side if you are worried about the dimensions, etc. This is the statistical mechanical quantity. It tells you how many degrees of freedom exist in a bottle of water. What you need to know is, if I give so much of energy, how does the temperature change, and measure temperature in energy units. Then it tells you a statistical mechanical quantity right from thermodynamic entities. If you multiply it here and do that, you are mixing it up. Okay, you are mixing thermodynamics and statistical mechanics, and which you shouldn't do. So this allows you to count the number of degrees of freedom once you know the right hand side. Now we have just said that if you can heat up something, it has microscopic degrees of freedom. I also said that you can heat up space-time. There are some observers who are going to see heated space-time. So can I count the number of degrees of freedom in space-time? Yes, you can. Just as Boltzmann could count the number of atoms, which is closely related to Avogadro's number, which again people didn't have any clue until we really understood the molecular dynamics. Even without knowing what those atoms are, the number of degrees of freedom which is needed can be counted. When you do that, you get a very beautiful result in classical general relativity. This is actually classical general relativity with H crosses thrown in appropriately, which will cancel out. Just like thermodynamics with K Boltzmann thrown in, which will cancel out properly. What you find is that if there is a region of space, normal space, three-dimensional space, and you have a surface, if there is some amount of energy in the bulk, then it is related by equipartition law, half kt, times the number of degrees of freedom. The number of degrees of freedom is the area on the surface divided by the Planck length square. I told you Planck length square is like 10 to the minus 66. So 1 square centimeter, a stamp size material, has 10 to the 66 degrees of freedom. What is more remarkable, there is a correspondence between bulk and the boundary. So the bulk energy talks to the boundary degrees of freedom and vice versa. And this is valid in any space-time which is static, which is in equilibrium. Now you go a bit further and you want to study dynamics. And what is driving the dynamics? It turns out that the dynamics can be expressed completely in thermodynamic language. The dynamics of space-time can be described, and space-time is some kind of a fluid. Its heating and cooling is what describes the dynamics, and that is proportional to the difference between end surface and end bulk. The degrees of freedom in the surface and degrees of freedom at the bulk, if they are not equal, it dynamically evolves this space-time. So all static geometries, I have told you, has these two equal, and that is exactly the other equipartition law written in a different way. What is crucial in this entire approach is that the gravity responds to the TS, the heat density, not to the energy density. It is intrinsically thermodynamic. And it turns out that the cosmological constant actually has this P plus rho equal to 0. So it doesn't contribute to the heat density. So the amount of cosmological constant you can never figure out from the gravitational field equation. It arises as an integration constant, and its value has to be determined by a separate principle, which we will come to. Now, what makes the space-time evolve? This one slide is for those who understand general relativity, others can just ignore it. There is a mathematical way of writing down the heating or cooling of the space-time depending on the sign, which is actually the time derivative of some canonical momenta, etc. And that is equal to the deviation from this holographic equipartition. If these two are equal, they are in holographic equipartition. Boundary and bulk are talking to each other, otherwise it doesn't. And this replaces the field equation of gravity. No geometry. It is purely a thermodynamic equation. And this implies and is implied by Einstein's equation. That is completely equivalent to it mathematically. If you use it in cosmology, it gives you something remarkably beautiful. So you take a surface like this in cosmology, and there is an n surface here, and there is an n bulk. And in cosmology, it turns out that the radius of a spherical region, if you think of this as a sphere, this result is in general, but in cosmology, if you think of it as a spherical region with a radius equal to what is known as the Hubble radius, which is built from the expansion rate of the universe, that is equal to this quantity. This equation is exact, and that replaces the Friedmann equation in this approach. And the universe's expansion is driven entirely by this n bulk by n surface. They also change with time, and when they are equal, you will get an asymptotic static situation. So this is all fine at some level, where we are only rephrasing Einstein's theory in a much more elegant way. And we are sort of discouraging people from go and apply quantum theory to Einstein's theory, just like you would have discouraged people from applying quantum theory to elasticity. But you actually have to ask the questions as to what happens in the truly quantum situation, which can be done, but it is a lot more technical. What essentially happens is that whatever is the dimensions of space-time at very large scale, when you go to very small scale, like in a collapsing black hole or towards the Big Bang singularity, etc., the system behaves as though it is two-dimensional. Okay? And the system also shows a tendency to store information in a fundamental unit which comes very naturally. The quantum information units is not bits like 2 or something like that, and the number which comes up is 4 pi. So roughly speaking, if it is two-dimensional, the simplest structure which emerges in that picture, this is, as I said, there is rigorous mathematics behind it, but I am trying to explain it qualitatively. The simplest two-dimensional structure which you can, smooth structure you can think of is the surface of a sphere with a radius equals LP, because nothing smaller than LP can exist. That will have a surface area which is 4 pi LP square, and if you put it in patches of LP square on the surface, there will be 4 pi of them. So it's not an integer, but you can always divide by 4 pi and define that as your one unit of information. This emerges from this particular dynamics. And one key lesson which comes up is that the Einstein's equation which we are talking about describes a thermodynamic equilibrium phenomenon. Now, if you take a fluid and you ask in fluid mechanics when thermodynamic equilibrium breaks down, there are actually two occasions where it breaks down. One is very familiar. You go to smaller and smaller scales in the fluid, molecules are moving around, you are approaching it at the mean free path scale. Then of course you can't use fluid mechanics. It is not a smooth continuum anymore. But there is one more scale. If you have, let us say, a tiny explosion inside water in a river, then that energy is injected and it is propagating. The moment energy is injected, thermodynamic equilibrium is disturbed, and that shock front is propagating. And over a period of time, the equilibrium will be reached inside. The place very inside will first acquire thermodynamic equilibrium. The surface region will still see the perturbation, and slowly the region in which thermodynamic equilibrium exists expands. This is what is happening again qualitatively in our universe. So the thermodynamic equilibrium describes the standard Einstein's equation which is so successful in cosmology, but that is in the region where thermodynamic equilibrium is applicable. If you go to very large scales in the universe, remember that diagram when we were looking at the sky, and if you are looking at quantum gravitational effects in the sky, at those scales, the thermodynamic equilibrium still hasn't taken place. So the approximate equation, which is the Einstein's equation, is not valid. There are corrections to Einstein's equation. This is a major paradigm shift in cosmology. In conventional cosmology, you write down Einstein's equation, you look at its solution, one solution describes a star, another solution describes a gravitational wave, yet another solution describes the cosmology, and you take what you want for your thesis subject. That is not the approach. You can take other things like stars or black holes or whatever, but cosmology is a different kettle of fish. Because in cosmological scales, at very large scales in the universe, Einstein's equations are not valid if this picture is true. We don't know what the correct equations are. We are just having guesses and we are trying to work it out. But the thermodynamic equilibrium gets violated at that stage, and the speculative idea, which is again backed by some amount of mathematics, but it is not as rigorous as everything I talked about today, is that it is replaced by a phase transition. What you call Big Bang gets replaced by a phase transition, and at very large scale, there will be a signature of this phase change. So let me explain to you that in the last part of the talk. I will just take a few minutes. So this is the expansion factor of the universe, which tells you how the universe is expanding, and this is length scales. So the first thing is that there is some epoch very much into the past where this is your so-called Big Bang. So that gets replaced by a pre-geometric quantum gravitational phase, where maybe space and time and these kinds of description is not the appropriate one. And the feeling or what this calculation suggests is that this description here is purely combinatorial. That is, you only have numbers and probabilities and combinatorial constructs like statistical mechanics, and you can study fluctuation from that. Then there is a classical phase here, which was originally radiation dominated, then it became matter dominated, and then it becomes lambda dominated. I don't need hypotheses like inflation in this. All the scale invariant perturbation will be generated from this quantum to classical phase transition. So is radiation dominated, matter, and lambda dominated, which is the cosmological constant dominated. So what you find is that there is something called a Hubble radius, which has this kind of a behavior. It is first increasing, and then when the cosmological constants start dominating here, it turns around and it moves like this. What is important in such a universe is that if you take an eternal observer, there is an observer who is sitting at the origin and he is waiting to get signals. He can wait to infinity and he will get signals only from this distance. That is, if he is sitting here, only from this distance. This curve sort of comes like this and then saturates. So there is a maximum, this is called a cosmic horizon, and beyond that you cannot get information. So the amount of information, and of course below this is quantum gravity, so no geometry applies here. So there is a nice window in which you have information contained, and all the cosmic information is flowing like this and crossing this Hubble radius. So there are various modes of fields or fluctuations, etc., which are going in. This is something which you are never going to catch. These two guys will enter the Hubble radius at some stage, and you can count them. This number we have called a cosmin, cosmic information, which is essentially the measure of the cosmic information, which is accessible to an eternal observer. It is computed exactly like d3x d3p upon 2 pi h cross the whole cube. You just do that calculation, and you can find that that cosmic information has a particular formula. Don't worry about this formula. But you can convert this, and this cosmic information, I have told you that the basic unit of information for you is 4 pi. So you just equate it to 4 pi and see what happens. If you equate it, you get a beautiful result which connects the cosmological constant lambda to the amplitude of fluctuations in the universe. Because it is the same phase transition which is generating the amplitude of fluctuation. So these two things which are completely unrelated in normal cosmology, because this comes from inflation and this is, God alone knows where it comes, we have no idea, we'll come back to it. after some time, kind of this is the standard per one. But here you can connect these two things and you get a formula with all these quantities, and everything else is known. Rho EQ is the quantity I told you, which is cosmologically determined. So the question is this equation true? This is connecting cosmological constants numerical value to the amplitude of fluctuation and other measurable quantities. And of course, I won't be giving this talk if it was not true. It is true. And if you graph it, you take the rho lambda observationally measured to its mean value, so that I have set it to unity, here I have set it to unity. It turns out that for an amplitude which is an acceptable middle value of the amplitude which is observed, I told you that it is like 10 to the minus 5. That curve, this is just plotting that curve, that lambda versus this one, that curve just coincide. These three curves cut at this point, which is non-trivial. Now, you can go and put error bars. Like for example, I have given sufficient amount of latitude in the error bar. This quantity is known, let us say, within 2 sigma in this band. This is known within this band. So we live in this part is the universe. Now, you also know what is the bandwidth on this amplitude. There are errors 68 to 84. So you get two curves. So our universe has to be within this if these theories are correct. When observations improve, if you find a point moves here, this theory is wrong. So this theory not only gives you the numerical value of the cosmological constant, it makes a prediction which in principle is testable. All you need is cosmology to get better and better, and this band to narrow down. If it narrows down here to a great accuracy, then the theory is wrong. If it comes here, of course, the theory is vindicated. So it actually makes a quantum gravitational observational prediction from these models. There is also another way to think about this, which is not my favored way, but many people like it. So let me explain this to you. So you take rho lambda, rho EQ, both are determined by cosmology. This is the amplitude of fluctuations in the universe. This also you know. You compute this quantity. This is absolutely crazy quantity, 2 over 3 pi, there is a logarithm, this k1 is this number. You plug in all these things and compute. You find its value is 4 pi. Okay? Now, how accurate? It is 4 pi to 1 part in 1000. Because there are observational errors in this, but there is a logarithm which saves you. So when you put it in, it is equal to 4 pi for 1 part in 10 to the minus 3. Now, I will leave it to you to take an opinion as to whether a crazy combination like this, which no one could have thought of without a theory, being equal to 4 pi requires an explanation or not. This theory gives you an explanation, or you can say that it's just a coincidence, it's just 4 pi. There is no explanation is needed. That is up to you. So just to sum up, the first point, which I didn't sort of crow about, but which is something which shouldn't be missed, is that in cosmology we do understand the evolution of the universe from a fraction of a second to 14 billion years. This is extraordinary achievement by the standards of science in any branch of physics, if you just look at the scales in which we do understand things. Of course, all the interesting things are before that 1 second and after this 40 billion years, but still, it is a non-trivial success. We also have a picture that some kind of vacuum fluctuation generated in the early universe can act as seeds for cosmic structures, and that is how galaxies, etc., has formed. The major uncertainty is this cosmological, uncertainty meaning unknown parameter, is this cosmological constant, which is contributing anything from 69 to 71% to the energy density today, and that is accelerating the universe. If you want to explain this, we most probably require a completely different paradigm shift. That is, a third avatar for the gravity would be required. Thank you.
Okay, so thanks a lot, Paddy, for this extraordinary talk on gravity and whatnot. So I think we can open it for a few questions from particularly students, if anybody is interested to ask questions.
Yeah.
So maybe you can mark.
I think they're bringing the mic, or I don't know.
Is the mic? Oh, yeah, a lot of mics. All of them work.
Thank you. My name is Ganesh Rajaraman. I work at the Institute for Plasma Research, a nearby institute. Actually, I started attending your school when I was a student in IAC, summer school, way back.
Okay.
And I also use your physics reports to teach StatMech to my PhD
StatMech of
students.
gravitating system.
Yeah. Toy problems, two problem problems.
Yeah.
So it's an excellent talk, as usual. Nothing less can be expected from you. Thank you very much. So this association of emergence, gravity as an emergent phenomenon is quite stunning. So you're basically associating a sort of temperature and a heat-like concept to vacuum fluctuations.
And not even vacuum fluctuation, to space-time itself.
Space-time itself.
Yeah.
And then from there you're saying that so you don't have to think of
so you just write down the thermodynamic equations for this fluid, which we call space-time. And there are underlying degrees of freedom which we have no clue what they are. So we are at the same level as Boltzmann, who did not know what molecules were.
So, right.
So and then you write it down.
Question is there a very specific prediction that comes from this calculation?
That is what I said. In cosmology, it predicts the value of the cosmological constant.
No, more observational kind of thing, which...
This is observational. This is what you measure. So for example, the previous diagram which I showed, there is a particular combination of cosmological parameters. Let me go to that. So this particular combination is purely observational. Every quantity there, like rho lambda, rho eq, A, and this is just the Planck energy, which is G, H cross and C. These quantities are measured to enormous level of accuracy in cosmology today. And that has been the success story of the cosmology. But nobody thought that this particularly weird combination, nobody would write down this on fresh morning. This particular combination should have a value 4 pi. That is a prediction of the theory. Okay? And turning it around, you can say that it gives you the value of any one of them if the others are fixed.
So I had one quick question. So this is interesting because you are not saying what we usually say in high energy physics, if you probe beyond a certain length, something new will appear.
Yes.
You're saying that the whole paradigm itself has to be replaced.
Absolutely.
So if that is the claim, one should be able to understand some of the classical successes of JR, like calculating the perihelion of Mercury and things like that, using your picture. So how would one understand?
That is very easy because classical GR corresponds to thermodynamics. So this is like trying to understand everything about what steam James Watt did or steam engines did or whatever was studied in thermodynamics, Clausius and all these guys who had no clue about the molecular structure of matter or what heat is. They had a calorific model of heat and all kinds of crazy things. But thermodynamics had its domain of validity, and within the thermodynamics, when you don't take fluctuations too seriously, you don't worry about Brownian motion or you don't worry about all kinds of things near phase transition, it's a very successful theory. Perihelion precision and all these things belong to the thermodynamic equilibrium of space-time. And there Einstein's equation is exact. There is corrections are tiny. It is like fluctuations are very tiny. It is like 1/√n. Okay. So that is why it comes. So it can only be tested at the center of a black hole where collapse is occurring, or at Big Bang, what replaces Big Bang, and what is the value of cosmological constant. These are the three questions which I pointed out. So cosmological constant and what replaces Big Bang, we have a fair picture. Cosmological constant, plunk on, we have a rigorously mathematical result. The phase transition, it is still speculative, but there is a kind of a notional picture which tells you what is happening. Center of the black hole, we are still working on. What happens is that this gives you a 0-point length to the space-time, and that is where the collapse sort of stops. But universe is easier to understand than a black hole because black hole is not homogeneous, while the universe is. So mathematics is easy.
So my name is Om Trivedi and I'm a physics student, and I'm very grateful for your lectures on Maxwell's equations and that Fourier transform thing. So my question is that in your theory of thermodynamics and gravity, so there are so one of the main problems that you have addressed is the dark energy issue. So I've heard that there are some other theories like modified theories of gravity which attempt to explain it. So how does your theory like reconcile with those theories?
Okay. So, in my approach, I had always believed, and I continue to believe, that a cosmological constant is dark energy. That you don't need to modify gravity except by addition of a cosmological constant, which is a very trivial modification of gravity. That is not what people mean when they say modifying gravity. Or you don't have to bring in things like or you don't have to bring in things like quintessence or other scalar fields, etc. Now, this is a question which ultimately has to be decided by observation. The cosmological constant has a particular equation of state using a parameter called W, which will have -1 value. And on several occasions, I have taken bet and made money by saying that observations will continue to prove it W is equal to -1. So now people are not taking the bet, so it has sort of come down. Okay. So, but if observations tell you it is not there, then we have to, all this is wrong. I mean, wrong meaning I can modify all this to accommodate quintessence, but it is no longer very elegant. So I won't do that. But the other theories, the more serious problem is that if you use modified theories or quintessence, you still have to explain why the cosmological constant which I add to Einstein's theory is 0. Or why that combination gives you a particular value. So you don't solve cosmological constant problem. That will still remain, but you may solve the dark energy problem. But this question has to be ultimately answered by observations. Yeah.
So my question is from this slide only, and I am understanding it wrong, but it somehow I can understand the rho lambda rho EQ, the amplitude fluctuation, everything is coming as an observation. But it's not like that you are just want to cook up the number and putting it in a very complicated combination and cooking up the number 4 pi to make it.
No, I mean, I told you the theory from which this number comes. You see, the theory starts with something called the total information content of the universe, which you can compute. And then you compute that, and then you can do two things. You know the information content accessible to an eternal observer. There is a formula for that. Then either you can feed in all the information we have about the constants. So this is the information accessible to an eternal observer. This is the formula for that, which comes from theory. Then I can plug in these values and ask what disease. And it turns out that it is 4 pi to an enormous accuracy. At that stage.
Even the K1 part also.
Sorry?
The K1 also comes from the
K1
theory.
also comes from theory. I mean, you think early in the morning I will write down numbers like 2 to the 1/3 and 3 to the 1/2. Okay. So this also comes from the theory. Okay. And so you have this number, and then you find that it is 4 pi. Now, the way I would approach it is completely different, because I have a completely different quantum gravity paradigm in which the two-dimensional structure at Planck scales tell you that this has to be equal to 4 pi. Therefore, I will not do this approach at all, and instead I will write that equation the way I did it here. Okay. Here this 36 pi square is actually some 4 pi has already gone in. There is a 9 pi and a 4 pi which has already gone in. I will write down this formula and I will tell you that I have determined the value of lambda. But depending on your point of view, you can take either one of them.
So with this, do you rule out all the correction to Einstein-Hilbert action?
Einstein-Hilbert action?
Yeah. So
No, because if Einstein's theory is just a thermodynamic limit, first of all, you shouldn't talk about Einstein-Hilbert action. You should talk about at the level of field equations itself.
yes.
But Einstein-Hilbert action can be interpreted thermodynamically. It turns out to be the free energy of the space-time. Because in Einstein-Hilbert action, there is a surface term and a bulk term. The surface term will give you the entropy, and the bulk term will give you energy. And totally, you will get some E minus Ts, which will be the free energy of the space-time. So when you are extremizing Einstein-Hilbert action, you are essentially extremizing the free energy of a thermodynamic system, which is what you do.
Any other question?
Yeah.
So in the regime where gravity is just thermodynamics,
Right.
the nature of your space-time atoms do not matter. You're just counting things.
That's right.
So if I were to understand correctly, so if there are these sort of center of a black hole, there are situations where the nature of the space-time atoms could become important.
Correct. Yeah.
So now, in the theory that you've developed, what sort of assumptions do you have to make regarding the nature of the space-time atoms in those regimes?
Okay. So what one is trying to approach here, in contrast to all other models of quantum gravity, is an admission that we don't understand these things, so we have to go top down. Top down in length scales, not in energy scale. So I start from classical gravity, then it tells me that I am thermodynamic. Then I rewrite classical gravity in thermodynamic manner. The next stage I didn't describe here is kinetic theory of space-time. So you can actually write down a distribution function for the atoms of space-time, and there is a new variable which comes in, which happens to be a null vector, which is like the momentum of these unknown degrees of freedom, but it carries an extra variable at every point, and you can write down a dynamical equation for that. It so happens that this equation is horrendously complicated, as you can imagine. So getting information out of that in general, when it happens very close to some singularity, etc., we have not been able to do this very successfully. So we have to make some extra assumption. The usual assumption which we make in cosmology is homogeneous. It is homogeneous and isotropic. Then things become much simpler, and then you can handle this. So the cosmological part is easy. Then there are some trickeries which one can do, like you can think of a black hole collapse, not from normal matter, but from a dust collapse. So the dust collapse interior solution of a black hole happens to be the same as cosmology. So you can make some progress there, but that is not enough. So we have to come up with new techniques to do that.